Hey, happy Monday. Good morning. And go Badgers on Wisconsin. Well, hope everybody's back and rested, had a good break, and are ready to go with some mathematics here in Algebra 2. We're going to start a new chapter, and our first section, as you can see up here and in your note sheet, is called Introduction to Sequences. What I like to say about a sequence, kind of as an introductory, is this that a sequence is really an ordered set of numbers. Okay, and that ordered set of numbers could be like 2, 4, 6, 8, 10, 12. Notice it goes in order. There's a sequence, and there's actually a pattern to this list of numbers or this sequence. All right. Each number in the sequence is a term of the sequence. A lot of times you'll see the first term represented by an a sub 1, which in this case would be a 2. The second term would be a sub 2, which would be the 4. The third term would be a sub 3, which would be a 6. So notice that notation is going to be very important to understand. You can also have two types of sequences. The first type is an infinite sequence that continues without end. So if you think of the natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, and if that would keep going forever, that would be an infinite sequence. Just 1 second. All right. The sequence that I drew up above here, 2, 4, 6, 8, 10, 12, that sequence would be a finite sequence because it stops at 12. It only has 1, 2, 3, 4, 5, 6 terms. So you have an infinite sequence and a finite sequence. Excellent. All right. Now, what I'd like to do is introduce you to an interesting special sequence of numbers that we can work with, named after a famous mathematician, Fibonacci. The sequence goes 1, 1, 2, 3, 5, and as I'm writing these, see if you can see the pattern here. 8, or how I'm generating these numbers. 13, 21, 34, and that pattern continues. Not sure if anybody can see the pattern. Feel free to pause the video if you'd like and have someone share if they can see the pattern at this point. So looking at this famous sequence at the top, the Fibonacci sequence, what a great word, Fibonacci. We're going to talk about some terminology that goes with sequences. A sequence can be thought of as a function. So this series of numbers, okay, can be thought of as a function. Every one of these numbers is a term, remember, with a sub 1 being the first term, and that is equal to 1. A sub 2 then, 1 second here, I like how this is spaced, so let's put some space in here. There we go. Thank you for your patience. A sub 2 is the second term, and a sub 2 is a 1 in this case. A sub 3 is the third term, and in this case that's a 2. And we could continue this pattern. If you notice, the term numbers are represented by n. So this little n at the bottom, a sub n, means whatever term we want it to be, the nth term, and a sub n would be the nth term. Now notice, because it is a function, each number n, if you take a number n, it only points to one term in the sequence a sub n. Okay, so it's very important to get this notation down. Every term is represented by, again to review, a sub 1, a sub 2, a sub 3, and the 21 is actually a sub 8. So very important notation. Now, that's the background of sequences. Let's take a look at some let's take a look at some more, I guess, notation and how we're going to read these. So notice up here, again, we're working with this Fibonacci sequence. Okay, if you notice in the table, I have n as the first term, and a sub n, which is a sub 1, is 1. A sub 2, a sub 3, a sub 4, a sub 5. The domain are the n values, first term, second term, third term, fourth term, fifth term. The range are the actual term values. So the first term is 1, the second term is 1, the third term is 2, the fourth term is 3, and the fifth term is 5. Again, when you see the subscript, you use the word sub, so a sub n. Okay? Now, a recursive formula is a way or a rule in which one or more of the previous terms are used to generate the next term. So, if you notice this pattern up here, to generate the third term, a sub 3, I'm actually adding together a sub 1 plus a sub 2. So 1 plus 1 equals 2. To generate the fourth term, I'm adding the, second term plus the third term. 1 plus 2 equals 3. To generate the fifth term up here, okay, I'm taking the third term plus the fourth term, so I'm taking a 2 plus a 3 to get the 5. That's called a recursive formula because I'm using previous terms to generate the next term. Okay. Now, if we're going to write this as a formula, the next a sub n term would be equal to a sub n minus 2, 2 terms ago, plus a sub n minus 1, the previous term. And there's our formula. So if you notice, this matches up. If I take a look at this, let's extend the page a little bit. A sub 5 would be a sub 5 minus 2 plus a sub 5 minus 1. This is if we're trying to find the fifth term. That would mean that a sub 5 is a sub 3 plus a sub 4. And that's exactly what we got up there. So awesome. Using the previous two terms, 1 plus 2 is 3, 2 plus 3 is 5. Using the previous two terms to get the next term. Moving on. Again, feel free to stop the video whenever you would like. Alright, back at it. Now let's look at some examples of how we find terms in a sequence. So this says find the first 5 terms of the sequence. So in other words, n is going to be 1, n is going to be 2, n is going to be 3, n is going to be 4, and n is going to be 5. Okay? This is called an explicit formula in this case, and it allows us to find any term. Oops, sorry about that. In the sequence without having the previous. Okay? So it's different than a recursive. So if I, for instance, want to find the first term, I just have to plug into my formula. First term, n is 1. So in my formula here, 3 to the n minus 1, I'm just going to put in a 1 for n. 3 to the first minus 1 is 2. I can jump down here and find the fifth term, 3 to the 5 minus 1. So I can find any of these on their own. 3 squared minus 1 is 8. 3 to the third minus 1 is 26. 3 to the fourth minus 1. Alright, so continuing on, 3 to the fourth minus 1 is 81 minus 1, which is 80. 3 to the fifth minus 1 is 243 minus 1, which would give me 242. So the first 5 terms I would write out with the commas: 2, 8, 26, 80, 242. So it's a matter of making a chart, please. I will be asking you to show this work. So you must have a chart. And letting n equal 1 through however many terms. In this case, the first 5 terms, and showing your work on how you got those. Okay? Another example quickly. Again, feel free to pause and get everyone an opportunity to get this work down before we move on. Find the first 5 terms of the sequence, so make a table. Again, chart required. First term, second term, third term, fourth term, fifth term. And now we have to put in a 1. 1 squared minus 2 times 1, negative 1. 1 squared minus, 2 squared minus 2 times 2. That's 4 minus 4 is 0. 3 squared minus 2 times 3. Notice I'm putting in n in my formula wherever I see an n. 9 minus 6 is 3. 4 squared minus 2 times 4 is 8. And 5 squared minus 2 times 5 is 15. So the first 5 terms written in sequence form: negative 1, comma 0, comma 3, comma 8, comma 15. Awesome. Alright, so those are explicit formulas. Let's look at a couple of recursive formulas. Now, recursive formulas are formulas where you're going to have the first term and you're going to have to use the previous term to get the next. next term. So notice the formula here looks a little different. We're always going to be given, in this case, we're always going to be given the first term, and then we're actually going to be given a formula to find the nth term. But notice, in that formula, the a sub n minus 1, because it's n minus 1, that's where we're going to plug in the previous term, whatever that previous term is, and then we're going to subtract 8. So this formula is really the previous term minus 8. That's kind of our rule or our pattern for this formula. So notice when I start my pattern out, I have to start with the first term, or n equals 1. I can't jump around and go to any other one. Well, that's given to me. Okay, we know right away that the first term is negative 5. That's a given. That's given to me over here. Okay. Well, to get the second term, I'm going to need the previous term. So remember, this column, the a sub n minus 1, is the previous term. So the previous term here is negative 5, right here. My formula says take the previous term, okay, to get the second term. It says take the previous term, which is the first, and subtract 8. Now I got negative 13 for my second term. Okay, now I'm going on to my third term. I'm going to take and bring down the previous term right here, negative 13. And the third term says take the previous term, which is the second term, negative 13, and subtract 8, negative 21. And this pattern continues. I'm going to use the previous term, negative 21. Find the fourth term. I'm going to take negative 21, and I'm going to subtract 8 to get negative 29. Continuing on, I'm going to bring the negative 29 to find the fifth term. I'm going to take that previous term and subtract 8, and I'm going to get negative 37. So when I write out the first 5 terms using commas, negative 21, negative 29, negative 37. Again, feel free to pause. We're getting close to the end, but feel free to pause at any time so that students can get caught up. You can rewind, clarify anything. Awesome. All right, here we go. Again, we have a recursive formula. We're given the first term, and we're given a rule that uses the previous term. Okay, so you can see that information right here. There's the first term, and here's the rule that involves the previous term. So first term, n equals 1, is given to us. That's negative 2. Notice, if I kind of write this out in words, a sub n equals 3 times the previous term, whatever that is, plus 2. Kind of reading it to you, wherever I see the a sub n minus 1, that means the previous term. Okay? So let's take a look at how we fill out our chart here. The second term is going to use the previous term, which is going to be continuing on. So a sub n minus 1 would be a sub 1, the previous term here, 2 minus 1. We know that to be negative 2. So my formula for the second term is going to be 3 times a sub 1 plus 2, which will be, the second term will be 3 times negative 2 plus 2, which is negative 6. That's going to be negative 4. Okay. Now if I want the third term, I'm going to use the previous term, which is a sub 2, which is negative 4. And my formula says to get the third term, I take 3 times a sub 2 and add 2. So that's going to give me 3 times the previous term, which is negative 4 plus 2, give me negative 10. The fourth term, I'm going to need the previous term, the third term, which was negative 10, because the fourth term is going to be 3 times the third term plus 2, or 3 times negative 10 plus 2 for a negative 28. And the fifth term, I'm going to have to use the fourth term, the negative 28 that I just got, because the fifth term is going to be 3 times the fourth term plus 2, or 3 times negative 28 plus 2. Whew. Big numbers here. 28 times 3 is negative 84, plus 2 is negative 82. So there's a good chart. And so when I write out my answer, I make sure I write it as a sequence. There we go. Negative 2, comma negative 4, comma negative 10, comma negative 28, comma negative 82. Alright, moving on. Now, the last two examples, we're going to kind of play Jeopardy and work backwards. We're going to actually have the sequence, and we're going to try and find the rule. Okay? So we're going backwards. We're going to try to take the sequence and go backwards and actually find the pattern, or what I like to call the rule. Okay? And there's a very specific way that can be very helpful for you to get these. And we know that it's either going to be linear, quadratic, or exponential. Okay? So linear, something times n. Quadratic, n squared, something involving n squared. And exponential is going to be something to the nth power. Okay, it could be like 2 to the n, it could be 3 to the n minus 1, something of that nature. There are other ones available. So what we want to do is take our terms that are given to us, 5, 10, 20, 40, 80. You may see the pattern. But first of all, subtract and take a look at the differences between these. Okay? So the first differences are not the same. Okay? 10 minus 5 is 5, 20 minus 10 is 10, 40 minus 20 is 20, and so on. If those aren't the same, take a look at the second differences. 10 minus 5 is 5, 20 minus 10 is 10, 40 minus 20 is 20. Those are not the same. So, first differences is linear. It's not linear. Second differences are quadratic. It's not. Those aren't the same. So finally, I'm going to look at the ratio, or I'm going to divide. Okay? So 10 over 5 is 2. 20 over 10 is 2. 40 over 20 is 2. And 80 over 40 is 2. If the ratios are the same, then we know that it's exponential. So a lot of times I take a look at this first term and it's going to be something involving perhaps that first term. Okay. Alright, so as I was saying, when I look at this pattern, I can see that it looks like these are kind of multiples, somewhat, I guess, multiples of, a lot of them are multiples of 5, but also, if you think of it, 5 times 2 is 10, 5 times 4 is 8, is 20, 5 times 8 is 40, 5 times, what would that be, 16 is 80. So what ends up happening is, if I take 5 times 2, that gives me 10. 5 times 4 gives me 20. 5 times 8 gives me 40. 5 times 16 gives me 80. Notice that 2 is 2 to the first. The 4 is 2 squared. The 8 is 2 cubed. And the 16 is 2 to the fourth. So I can write, and the 5 times 1 is 5, and the 1 is 2 to the 0. So this formula starts out with a 5, and then we're multiplying by 2 to the n minus 1. So here n is 1, notice, and the 2 is to the 0 power. In the second term, the 2 is to the first power. In the third term, the 2 is to the second. So we're always 1 less than what term we need. And there's your pattern. I did the tough one first for you. Okay? Again, pause at any time. One more example. Thanks for your patience. Now here, again, we have our sequence, and we're looking for the rule, or what I call the pattern. Okay? Remember, it could be linear, first difference, quadratic, second difference, and if it's a ratio, whoops, my bad. Can't do that. Just made the video a little longer. If it is a exponential like the last one, then you have the same ratio. So I'm going to look at the first difference here between these terms. 2.5. Oh, look at here. 2.5. Oh, look at here. 2.5. Look at here. 2.5. First difference, that means I have a linear pattern. With a linear pattern, to get the formula, you know you're going to have the first term, and then we're going to add in that first difference always times n minus 1. This will always work for linear patterns. So again, to get this, what I did was I took the first term, let me write it this way. I took a sub 1 plus the difference times n minus 1. And in this case, the difference is 2.5. So what I'm going to do to finish up is I'm going to do the distributive property, 2.5n minus 2.5, and get my final formula, 2.5n minus 1. And there you go. Last example. Alright folks, I know that was a little long, but why not? Coming back from break, all craving mathematics. and a big Wisconsin win and a big game tonight. But here we go. Finish up. Here's your assignment. You got a worksheet. 12-1 practice B. As always, enjoy. All right, bring your questions tomorrow. Thank you.